Whereas just counting the number between you and you let's go. Thank you. I'm gonna start both the midterms after this. Both after. Start at 5, finish at 10. How are you? Ready? I'm doing the same one. Yeah. I think what it's saying is that you look at that. It's like part of exactly. Yeah. Well, they both have it. He died in his Michael. Oh my God. When I So I was like, I swear to God, I did like
That would just be funny. It makes sense, you know, I kind of like singing.
yeah, but you said like,
Medium resolution, low res today. High power.
All right. All right, everyone. Let's get the lecture started. So today we're going to mainly talk about the exam 2. We're going to give you like a quick review over the mainly the 4 topics that we go through the second half of the class, and then if you have any questions regarding homework or exams, feel free to come to me after the lecture. We also have the open labs today after lecture at the lab space, as well as tomorrow at 11 a.m. So in case you have any questions. Also, Piazza is always the best place to ask so that your classmate can also share some of the knowledge. You're not competing with each other. We're just, well, you're all against me, so you're not competing with each other. A few announcements. The homework 7, the solution has been posted on the website, and and you have done all the homeworks for this class. So congratulations, no more homework from this point. The important things here, the exam 2 are going to happen tomorrow from 4:30 to 6:30 p.m. For everyone who starts at regular 4:30 p.m., you will be sitting exactly as last time. We have 3 lecture halls assigned, lecture classrooms assigned for the exam. Just as before, sitting 1 seat in between with each other. For those who have additional accommodation requirement, if your starting time is at 2:30 p.m., please go to the BBB 3941. And if your starting time is at 3:30 instead of 4:30, then you go to the Dow 1023. If you're not clear when is your start time is, email us, and I mean you should know. But we will send out another email tomorrow morning just in case, so that everyone knows where your starting time is. And the exam 2 data sheet will be posted after class today. Feel free to go through them before the class. Please do go through them before the exam tomorrow and post any questions or things you're not sure about on the Piazza. We'll try to answer as many questions as possible, but we're also, there might be some question we are not able to answer. We'll just let you know as well, but without providing any answers. Yeah. And as I said, we have the open labs today after lecture and tomorrow at 11 a.m. for any of the questions you might have. I think today we have open lab until, if I'm not mistaken, 9 p.m. today. So yeah, that's a very good place to check out after this class if you have any questions. Another thing is we will have the student presentation starting next Thursday. The attendance of these are still required because the grading actually combined with from our side as well as 25% from the classmate. Again, you're not competing with each other. Just give your honest feedback and rate the presentation as the quality as it presented. The topics are already being assigned, but we will share more information on the schedule, etc. After the exam, so that we don't have to worry about that for now. But the topics has been assigned. A little bit logistics to just reiterate: it's closed book, closed note. You will be provided with the data sheet and during the exam, and then we might have some dynamic changes on the data sheet during tonight after we release it to you, so that if anything anything that we feel like would benefit for you guys for the exam, we would make the edit before the tomorrow's exam. We will not change anything during the exam. So yeah. And you're allowed to bring calculators of all forms, but you're not allowed to store any notes on it. Also, it's a very small screen, so probably not worth it anyway. And you're not allowed to borrow calculator from each other for obvious reasons. If you do need anything, come to us during the exam. Maybe we can do the calculation for you if needed. But the calculation should not be too bad. If you're having like an absurd number, you probably get it wrong. Just do it again. And the phones and other electronic devices has to be stay in your pocket at all time. Some of the rooms might be a little bit compact, so just behave yourself. So, and the timer and clock will be made available, just like last time. We will give each lecture room exactly when you guys started, and then have the end time to be 2 hours from that point. So if you started a few minutes late, that's totally okay. You would just finish a few minutes late as well. Some of the strategies here, as before, do not spend any time, too much time on any specific questions. You do have to show your work and statement your assumptions. This is like a good way to get some partial credits in the end. And if you don't show any work, partial and just the answer, and the answer is wrong, then it's very, very unlikely that we can give you any of the partial credit. Yeah. So this is just something that I mentioned before. And what to study here? Well, homework and labs, also the old exams on the website are the best resources for the class. The questions are pretty much going to be like the homework and midterm. There will be no surprises, nothing fancy, but the design question might be a little bit long. So, make sure you have enough time for the design question. I think a rough estimator would be, you should probably at least have like 40 minutes saved for the design questions. We will recommend you to have 1 hour, but that's just a rough timeline on how you should, or how you are recommended to divide your exam time. The previous questions are not as long, but the design questions does require some readings. Make sure you read through everything before you start the work. And one more thing. So for this exam, we're doing something slightly new. Basically, the whole exam going to worth 105 points. The 5 points being like extra, so we'll cut it off at 100. But we do not give any specific questions as a bonus question. So you do have to work on every question. It's just everything added up together ends up being 105. Make sure you work on all the questions together, and in the end, you will be adjusted based on how many. Yeah, you get the idea. Any questions regarding that, or any of the materials to go through? Or any of the logistics? Okay, perfect. So, topics to cover. This is not like a complete list, but it's pretty much, it's basically majority of the stuff. So technically, we will cover everything in class so far, but realistically, it's going to be heavily focused on the second half of the class, basically interrupts, timers, serial communication, as well as the analog signals, ADC and DACs. We're going to have like a couple multiple choices for those previous topics in the multiple choices, but that should be the majority part. You might need some basic understandings of those in the design questions as well, naturally, but the remaining part should be much heavily focused on the second half of class. So let's jump into the interruption review. This is a little bit long time ago. So basically, how interruptive works from a very high perspective, from a very high level, is that those peripherals, for example, GPLs, they have like embedded hardwired interrupt wires that connect it directly to the chip. So anything that happens as you programmed it, any event that raises like a certain critical flag, that got passed directly to the chip, and then that caused an interrupt in the main program to jump off to the handler mode to do whatever is assigned and then go back. So this is like a little bit detailed view. So you have the signal coming, in this case, again, GPLs. It goes to the NVIC, the interrupt controllers, and instead of this interrupt controller, you will go look into the interrupt vector table. which stores in the memory, just like a lot of other things as well. It will basically look at by the index of that interrupts, which is hardwired to each of the GPIOs. So it knows exactly what number is, and then find where that location is inside of this interrupt vector table. And then once they find that, it will basically point the processor or the program to whatever the address that's stored at that interrupt location. So just give you a little step view. Signal goes in and then goes to, for example, we have like a request 9, and then it will find that inside of the vector table at exactly 9. Each of them have a hard-coded address inside of the vector table. And then after that, you look at where that is pointed to. This is like a quick, formula here that might be handy, but basically is pretty much all of them are like 32-bit. So every time if you have like an index up in terms of the interrupt index, you would basically times the 4 and then plus to wherever the starting of your interrupt table inside of the vector table. And then once it located that location, it will basically look at what's the address stored in that location and then jump to whatever program or handler program or functions that's being pointed to. So give you a little bit more visual representation. This case, we have like a I3, like the X3 coming, and then it pointed to look through the table, and then it located itself there, and then that location points to a handler function that's being implemented at that location. So that function is basically where what's your job is. You write those functions, and the address of this functions will be stored at this table, essentially. And then just give you a little bit more. So say if we have this interrupt coming in, right? And then we look at the table, find that is the address inside of the vector table, and then that function corresponding to the function on the right, which starts at the address, say 0100000800. How would you actually do it in the program to assign where you currently make sure the program goes from the thread mode go to the handler mode at the right function? So this will be the function how to do that in C code. Basically, you put whatever the address that was the starting of that function that you wrote, the handler function, to the address inside of the vector table, which is this one, which is and this can be calculated based on the index of that request. So for example, if you have, say, the interrupter number 9, then you start at the address and then plus 4 times 9, and then give you an address, and then you fill whatever that handler's function's address to that location. This is kind of important, so remember that. Yeah. Okay, so we have interrupt request coming in, right? The MVAC gonna look through the vector table based on essentially the index of this interrupt request, right? And then that address can be calculated by something similar to this. And then we find that location, and then we will look at where to go, right? In that location, we're gonna store an address for whatever handler function you're gonna go through for your interrupt. And say that address is that. And how would you actually implement that in the code level? This is how you will implement that. Essentially, put the address of the starting of that function to the MVAC address inside of your MVAC table. Is that clear? Hopefully, yes.
So for the calculation, is it like on the previous slide? Is it 64 plus 4 and then that entire 8 times 9, so 68 times 9, or is it 64 plus 4 times 9, which would be
Wait, what's the first version?
Do you do 64 plus 4 and then do 68 times 9, or is it 64 plus 36, like 4 times 9?
Okay, so the question is how we actually calculate this. So we do, in this case, it's 64, but it could be a different number, but basically wherever the number of your starting point at, and then you use this number plus the 4 times the number of the index of the request, and then get the actual number. No problem. Hope that's clear. Any questions regarding the interrupt MVIC part here? Okay, perfect. So how is it worked from like a software and hardware level? Let's first look at the stacking and non-stacking. So basically, whenever a interrupt signal comes in, it would trigger what we just discussed, right? And then when that's been done with the program, before it jumps into wherever the address of the handler function it's pointed to, it will basically first stack all the relevant registers, I think in total 8 registers, into the main stack before the interrupt handler function happens, so that once they come back, it knows where to reload all those values back and then carry on its original functions. So after that, basically, after the handler function is being finished, it will be like an exit interrupt command, and then that will cause the first unstacking, essentially, unstack all the values you popped in there earlier, and then you carry on with the program. These are automatically handled by the MVIC, so you don't have to worry too much how exactly they work, but you do have to know when it happens and why it happened or why it doesn't happen in that case. For example, we just basically talked about this. Like this is the whole process. So for example, if we have a single interrupt happening, basically we will have the just show that's the previous one, this one. But once we have multiple interrupts happening, then we have to figure out a way to make sure the stacking, unstacking, or the which interrupts is handled at its priority, right? I'm not sure if you guys remember from the lecture. So we have actually a few different types. This is obviously the easier one. Sorry. This is the easier one, and before we go into that, I think this is also kind of important. So how do we deal with multiple priorities? We have a table that sets the priority. Basically, we have the 2 numbers. One sets the group priority, and the second to basically the subgroup priority. And the important thing to remember is the smaller the number is the higher priority. Do not get that wrong. And when we have the concurrent or overlapping interrupts, basically there are 3 techniques we're going to use. On the preemption, basically you have like something more higher priority that's going to scoop out the location of the existing one or the ones that's pending before that. Or you have the tail chaining. Basically you have something that's the same, essentially the same priority level, but just happen same or lower priority level. So they kind of just happen in a sequence, as well as the late arrival. Late arrival is essentially, when you're just entering the handler functions, doing like stacking and stuff, and at that moment something higher priority happens. So that scoop out the this current pending interrupts with that one first, and then do the current ones. So we will keep the top 2 are like a little bit more important than the late arrivals, but let me give you a little bit more visual representation. So this is like the most simple case. We draw these figures. This is from the previous lecture. I think it's good to have it show it up again so that you know how these things, from like a hardware and software level, what's been happening from like from the execution timeline. This is like basically the easy case here, single interrupt, as the same as we showed in the previous slide. The signal comes in, and then we turn on the pending registers, indicating that this is the essentially this is the like interrupt that's currently happening, the 4. And then it will update the priority register here with the current priority level, and then put, oops, okay, let's see if this one, and also put the active there. You don't have to, well, you do have to know these, but these bottom part is a little bit too detailed, but it's still good to know. And then it will first do, it will do the stacking and then do the execution, and after it finishes, it basically unstack everything back and then update these registers or priority tables accordingly. And when we have, and go back to the main program, and when we have the preemptions, essentially, for example, here, we have something higher priority happening. So instead of going, let's see, so instead of doing the unstacking, it basically go directly to the next higher priority request, interrupt request here. So instead of doing like a normal unstacking here, like there, it actually does stacking again, which is, this is because the request happened right after it come back from the request. Sorry, this is because it's currently inside of these execution, and then we have a higher priority interrupts happening. So we are stacking the registers inside of this interrupt to the stack as well. Sorry if it's a little bit confusing. So basically, we have, essentially at this stage, we have two sets of registers being put in the main stack. First is from the main program, and then because there is a higher priority interrupt happening, instead of finish up the current interrupt with the lower priority, we do the stacking again and stack whatever inside of this handler function into the stack, and then execute it the higher interrupt. So that's why you will see two stack there instead of unstacking like before. And then once the higher priority interrupt being finished, we unstack the first part, which pops the first part, which is the registers used inside of the previous interrupt request 4. And then we finish executing the interrupt 4, and then do the final unstacking. Does this looks all good to everyone? Basically, you should know what's happening at the software and hardware level on these type of interrupts with different priorities. Any questions regarding the preemption? Yes.
Just specifically, when things count as pending is kind of confusing. If you are stacking something and another interrupt comes at the same time, then you have two things pending.
Yeah. So the pending, essentially pending is, you have something waiting in line, right? This will be high during like the stacking phase as well. So you could have more than one pending, and then it will be executed based on the priority, essentially.
And they'll both finish stacking before one gets executed, or not?
Wait, what do you mean?
Well, if there are two things pending, then you have two things you could stack.
Okay, so the stacking and unstacking, the stacking is only happened when it's at its term. So for example, the stacking happened on the request number 4. That's already when it's being active. That's when it needs to do the stacking. The pending, we don't have to do any stacking for those who are in the pending stage. It's only for those who are in the active stage. So the first stacking happened for the main program. That's because the main program is currently active, so to speak. And when it's being interrupted, so we need to do the stacking to save the previous, it's like a snapshot of what was going on before. And similar for the second stacking, this is because the request number 4 is interrupted by the request number 3 with a higher priority, so it haven't been finished. So we take the stacking there as a snapshot, and then, yeah. Any other questions regarding this type of, preemption? Okay. So we also have the tail chaining. Basically, this happen is, some other interrupts happen when the program is already doing something with the same or higher priority. Basically, whatever new interrupt that's waiting in line is not as critical as what's currently happening right now, or not more critical than currently happening. If they're the same priority, you basically just execute it by the number where it got in, etc. So again, if we look at this example, somewhere here at the request number 4, another interrupt request happened. But that interrupt request is at a lower priority. So it does not preempt the current interrupt request 4. So instead, it wait until it finished. But the cool thing here, something happened here is that it doesn't do the whole unstacking, because the program knows, or the MVIC knows, it would go back, or it would go to the handler mode, or go to another interrupt right after it finishes the current interrupt. So there's no point of unstacking what we have on the main stack for the program, because it's not going to return to the main program. So it's going to just do a little bump, doing nothing kind of there, and then finishes the interrupts with a lower priority or the same priority, and then do the unstacking at the end, and then go back to the main program. These things on the bottom happens on the software level. On the top is what happened on the hardware level. Any question on the tail chaining? Okay, I see a few hands. Yeah, okay. What's the question?
I see in the priority table that priority or interrupt number 4 and interrupt number 1 is like 10 and 6.
Mm-hmm.
How come those are tail chains that have the same priority?
The question is the priority number 1 is number 10. Sorry, the priority is 10, right? And the priority number for the request 4 is 6. So in this case, the priority number of the request 1 is larger than the request 4, which means it's lower priority. So that does not get to interrupt what's the current happening. It is important, this number, the lower the number is, more important it is. Because there's an end to how important things are, but you can go all the way to higher number. There's a reason why we used it that way. Otherwise, everyone's just going to do 9999 to their priority, and then nothing gets done. Any other questions? I think I see another hand somewhere here. Any other questions? Yes. Sorry, which one? Oh, you don't have to worry too much about that. Yeah, basically it tells you that all these they're all ready to work, essentially, all these interrupts. But yeah. Any questions on the tail chaining? Okay, cool. Yeah.
If we're given a problem about these different types of handling, are we allowed to assume that it's going to do nested and tail chaining and late arrival at the same time, or will it specify which one is being used?
That's a great question. So if you were asked such question, we will specify in the question, tell you that you should use these when possible. In real life, these things happened all at the same time. So that's going to be the assumptions, but we will make sure that's stated in the exam as well. So essentially, all these things, the late arrival, the tail chaining, and the preemptions happening at the same time. Just depends on what's the new interrupt's priority and when that occurred, which will lead to each of these conditions. Hope that answers the question. Any other questions regarding this? Okay, so we will dive into the timer after. Okay, cool. So yeah, this is the a very high-level review of the timer. Basically, we have the physical clocking, and then we have the prescaler, which divided the clock into the longer time intervals. Essentially, make the hardware clock usually into a slower clock for the later system. And then there's a counter, which is the time counter here, which is a special register, which runs freely, and if it's enabled, it basically automatically counts upwards or downwards under the clock that's inputted. So basically, just do the counting, and then it counted very accurately. And then whenever there is, say, actually, let me put out the whole thing. So while we're on the prescaler, that was the function used to calculate the frequency of what's the clock gonna be after the prescaler. One important thing here is you have like a +1 there. This is because that previously, people sometimes just input 0 to the prescaler number, and that breaks the whole thing. So in the actual system, you also in your calculation make sure you add 1 to the prescaler number to get the accurate converted clock from the physical clock. And then basically, we want the time counter. So basically, it will have another. You can set those counters to be something happens. When a specific number is counted, and that would be just happening on a hardware level in parallel periodically. So you don't have to worry too much on that in the software. And that whenever that occurs, it will trigger. Occurs meaning whenever there is a number that matches your desired number, that will trigger an interrupt, and then doing whatever functions that you assign it to. And we also have the CCR register, the compare and capture register. It's capable of doing capture and compare on input and output. In this case, we can first look at the capture side. Basically, this will be taking the input from the time counter, which is the clock, how long it is from the beginning of the program. And then if there is something, for example, a signal from the GPIO or anything comes in, and that can just make this register take whatever the current value inside of the time counter. And then that number, whatever you need to do with this, it can also be directly wired to an interrupt. So that can trigger another interrupt as well. You don't have to know too much detail on this, but it's still good to have a general understanding of how the time will work at this level. It's not super low level, but a little bit on this. Basically, this is essentially the capture mode I was talking about. It's usually used as input when a specific external event happen, which is what we showed here essentially. Something, for example, on the GPIOs or other peripherals, some external signal happens, and then it will cost the CCR, the register, to take the value from the time counter, which is what's the current cycle, how many cycles we have passed, and then use that to do whatever you want with that number. And if an interrupt is needed, that will cause an interrupt. And of course, we also have the compare mode here. Usually, this is pretty straightforward. You put a value inside of the CCR, and then you constantly compare the number inside of the timer and the timer counter and the CCR. And whenever that two value equals, an interrupt is triggered, and then you can decide what you want to do with this interrupt. This is a slightly more detailed view. Basically, pretty straightforward. You can have a comparator, and then the counter value versus the constant value you put at the CCR register. Any questions on this? Hope this is pretty straightforward. Okay, so yeah, there are also different ways of counting in the time counter. You can set it to be counting upwards, downwards, or up and down. Depends on how would you do this. A use case for this is, for example, generate a PWM signal. Essentially, what we want to do is this is for a up counting. So essentially, what we're going to do is we have some amount of time it stayed at high, and some amount of time stayed at 0. So how we're going to do this is basically we have the time counter here, or like the AAR register here to automatically doing the counting. Okay, in case this is not clear, so basically the time counter just keep counting on, and the AAR here is you give it a number and you count until that number and then start counting again. And whenever that changing happens, that's the point you can trigger an interrupt. So this is the output from the top one is the output from the AAR, basically at any given number, and then we give it like a cutoff value, which is essentially the value we're going to put in the, well, not in this one, the other one, the compare one, the CCR. And then whenever that number is reached, it will correspond to essentially how many percentage of your time is on the high, how many percentage of your time is on the low. And then that cutoff generates this PWM signal, which is, amount of time is high, amount of time is low. And this is for every period. The register there, the repetition counter register, is for how many of these periods that are going to make this cutoff happening. So for example, if you have that value to be 2, then you have you only have this one peak among with this whole time. I don't think you will be worried too much about the RCR, but it's good to know about the AR and the capture and compare register. Any questions on this, on the timer so far? Okay, perfect. Okay, let's move on to the serial communication, or communication in general, because the first thing is actually non-serial. It's called parallel communication, or it's a pretty, it's the way that when we need super high performance, super high high speed, and then super high bandwidth. So this is essentially you have one wire connected to 2 different devices or chips or whatever, 1 bit per wire. So and you do need the clock for this. So this essentially is mainly used for like very short distance communications, as well as very high speed requirement, high priority essentially. For example, like memories, on-chip memories, etc. That's typically what used this type of parallel communication. And next, we have a few serial communication protocols we introduced. In total, I think 3 of them. So first is the UART. It's used for, nowadays usually used for chip-to-chip communication. And then we have essentially these 2 channels or 2 wires on 2 devices, the RX and TX. The TX and RX, they connect to each other. Basically, the sending of one device connects to the receiving of the other device, and vice versa. And this protocol does not need any clock, and this is like a 1-to-1 communication protocol. Any questions on UART so far? And the reason why the reason we can do the non-clock is because they have internally agreed baud rate, essentially how fast these data should be transferred, and then they basically on the receiving side always oversample on the input signal, and then whenever it sees a edge change, let's move to here. Whenever it sees a starting bit, which is a edge change, it will start oversampling there, and then because it knows the baud rate, it will basically calculate how long that should be for like a 50% of that data width, and then use that as the sampling point from that point on. So you always sample at that point. So the worst case, you will have the sampling to be shifted by 1 clock cycle with the higher oversampling rate clock cycle. So that usually works pretty well. And the data frame here, normally, it's basically usually 8 bit of data, and then we have a parity check bit as an option. You can have it or don't. We do have 1 starting bit and 1 stop bit. it's important to recognize how they are connected. So, you know. And any other questions regarding the UART? Yes.
UART has like a specific baud rate.
Yeah.
So you have to like predetermine that. But I2C and SPI have clocks. So does that mean that their rate can like just change?
So the question is, the UART communication have a predefined or agreed baud rate between the two devices. How about like the I2C and SPI? We will talk a little bit in more detail later, but generally speaking, SPI, you can decide, you can to a certain extent decide how fast your clock goes, so that it gives you a pretty large range of possible clock you can manipulate with. I2C is a little bit different. The speed, to a certain extent, is actually decided by the passive components you put it on there. We're not going to test you how to calculate those, but the amount of passive, or the value of the passive resistors you put onto a I2C communication essentially kind of determines what's the data transmit speed. But yeah, this is for UR. Basically, they have agreed baud rate between, and then the device, the receiving end, does the oversampling once it sees the first, starting bit, and then finding the midpoint of each of the bit, and then start sampling from there. This is actual data that's happening. So essentially, whenever the system detects the first starting bit here, it starts doing the oversampling, and essentially it sample half of the amount of their agreed baud rate, and then use that as always where they're going to do the sample in the future data. And then in this one, it's basically, you can interpolate what's the data from that by where you actually sample it. And then we have, start bit and end bit. You should be able to read something like similar to like this during exam. So yeah. Any questions on UART? Okay, sounds good. And next we go to the SPI. So SPI here, basically, it requires usually four wires, not counting the power and ground as usual. Basically, we have the serial data out, serial data in, and then a system clock pin that's shared within all these peripherals, and a chip select pin. So the important thing here is, well, there's a few important things. I guess to start with, this is a one-to-many communication protocol. Usually you have like one controller or one master, and it's connected to and make controls to multiple peripherals or multiple slaves. The chip selector pin is usually, it's actually being reversed, but I don't think we're going to test you on that. But if you feel fancy, feel free to include that. But basically, usually we will have one chip select pin for each of the peripherals. That's how we know which of these signals are going to where. Because all the the serial data out and serial data pin is shared between all these peripherals. The chip select pin is how they decide, how it determines which peripherals this information goes to. Yes, what's the question?
So on the exam, are you going to write SDO and SDI, or are you going to write MOSI and MISO?
That's a good question. So you will not have to write that, but both of them will work. Just different ways of representing the same thing. The important thing, both in that the MISO label is less popular because of the full name. So yeah, but essentially the input and output is what's important in those names. What is the input of this device? If it's MISO, then it's master in, slave out. Then and if it's for example, this serial data out, it's from the perspective of this device. So, for this device, this is the output, essentially. And the serial device in SDI is from this perspective, this is the input for this device. Yeah, there was another thing I was trying to say. Oh, yeah. So this is the more traditional way to connect it, with the chip select pins to each of the peripherals. There's also other ways to do this. It's called daisy chain. I'm not sure how many of you guys remember. Basically, it's essentially using, connect all those peripherals into like a chain. Essentially, the input or the data in to, well, the data out from the first peripherals connected to the data into the second peripherals, and the data out from the second peripherals directly connected to the data in of the third peripherals. And in the end, if say we have 3 peripherals, the third data out connected to the data in on the SPI controller. So in that case, you only need essentially 1 chip select pin. And then the data got will be essentially passed back to the controller through the last peripherals. So you will have like a couple clock cycle delays, depends on how many of these you chained together, but that's also another possible configurations of SPI, daisy chain. Any questions so far on SPI? Okay, cool. Another, I think, a little bit confusing diagram, but there are different modes of the SPI clock. We have like the phase and polarity mode in this for the SPI. In total, we have 4 different modes, and the important or like the easy way to check is essentially first you can check the clock polarity, which the CPOL, which is whether it is top or bottom, and that was determined by whether the clock when it's idle is high or low. And you can see that by if say this figure is like much longer, you will see when there's nothing happening in the data, what's the stats of the clock. If it's high, then it's if it's high at the idle, then it means it's polarity to be 1. If it's low that means the polarity is 0. And then for the clock phase check, it's basically checking what time it samples the data. If it samples at the edge, or it samples at the ending edge, the rising edge or the ending edge. So that's the way you can check. You can also just look at what time it changes. If that changes and the clock was not doing anything, that means that's the stage where it does the data changing. But yeah, it's good to know about this, but not too much emphasis going to be on this. Any questions regarding this? Okay, so this is like a typical what it would look like on like a SPI transaction. It's worth to point out that the SPI transaction is a full duplex communication protocol, meaning the bidirectional communication can happen at the same time. Although in this figure, these two kind of like nicely shifted. This is for just show, it's for like showing, but they can actually happen at the same time. And you will see normally the chip select pin will be, stay low whenever this peripheral is the one that's being selected. And the S clock is the system clock that's generated by the controller or the master. It's going to be active during these data transmission stage, but stay idle, either high or low during the idle stage, and that corresponding to the clock polarity that we just talked about. Any questions so far? Okay, perfect. So next we have the I2C. So I2C is half duplex because meaning it can only happen at one direction at a time. Essentially, they can't happen all together. The reason for that is they're sharing the same data line, the SDA, and then the SCL is the serial clock line that's shared by all the peripherals, and this does not have any data in it, so to speak. So the data all goes through the serial data line That's why it's only half duplex. And by the way, the UART can be, for duplex, just depends on how you're wiring things up. You can totally have two wires, so nothing to stop you there. And because it doesn't need clock, so. Anyway, I think the thing, I think one of our classmates actually brought it up. So all these pings on the I2C, like the SDA and the CLs, are left as open drain, because so that the I2C can be used to communicate between different devices at different voltage supply to a certain extent. So you would need external, in this case, resistors to enable to have it to be pulled up when it's high, essentially. So yeah, another thing to notice here, if you put a pull-up resistor, that means the output is high when the GPIO pin was assigned to be 1. High meaning is whatever VCC or VDD you connected to. And the number of that resistors can decide what's the transmission speed for your I2C. But you don't have to worry about how to calculate these, etc. Any questions on I2C? Okay, cool. Yeah, this is just similar as before. All those pins are left open drain, so you need additional resistors to make sure they're not floating. And this is a timing diagram for the I2C communication. It's important to notice that the data line has to stay stable when the system clock is high. So that you see that we make a little rectangle here. This is because the edge was used as the start and stopping bit in the I2C communication. So whenever the S clock is high, if there's something happening on the data line, that will interpolate it as either starting or an end. And that will cause all sorts of confusion. So what's happening is the data changes, the data SDA, the data line, actual data bit changes on the line will be happening when the S clock is at low. So yeah. This is again basically a real signal, or like a real oscilloscope view of how a I2C communication would look like. And you will see the bottom one essentially is the, I believe, S clock. It looks a little bit narrower or pointier compared to whatever the data line on top there. So yeah, that's something good to know, I guess. Another thing is the acknowledge bit and non-acknowledge bit. That generally happens when that transaction is a success. That's the bit that's sent from the receiving end. If it's a non-acknowledged bit sent here, that means it didn't work that time. So do it again. A quick summary here. Between these type of different communication protocols, I included the parallel here. But do notice that this is not serial. The top ones are serial. We don't have to worry about the one wire configuration here. It's something that if you take, I guess, FPGA class, you would learn how to do this, but we don't have to worry about that. Nobody really used that. So the UART here, it's just remember that it's asynchronized, and then it's not too complicated, and it's good for device-to-device communication over like longer distance, so to speak. And for the SPI, it's one master, multiple peripherals, and they share the same clock, and it's basically 1 to n configuration. And then how do they decide which ones to activate is through the select wire, basically the chip select pins. And for the I2C, it's like end to end, basically. You can have multiple masters or multiple slaves all at once. And then how they decide which peripherals to trigger or to talk to is based on the address. So each of these devices have its own hard-coded address. So that's what's being determined. That's how they determine, where the data should go or where the data was from. Yeah, let me think. It also needs the clock signal. And for the parallel, it's basically, something that's extremely fast. And yeah, and it's usually one-to-one as well. But I guess, yeah. So any questions on how they compare to each other from like a high level? Yes. Is UR full difference? No, that's a very good question. So it can be, depends on how you interrupt, how you implemented it. So essentially you have two wires, one for this direction, one for the other direction. If you only have one wire, then it's half, but usually it's one direction. Right? I mean, if you only have one direction, then it's half. If you have two, then yeah. So it can support. Yeah, it's able to support. The UART is able to support for duplex. Any other questions? Okay, perfect. So next we're gonna dive into the ADCs and DSCs, which is hopefully are still quite familiar to you guys. We have a few different types of ADCs. The first ones we looked at is the flash ADC. It's very fast. It's basically a voltage divider from whatever the reference or the voltage in to the ground. And then usually we use the same value of the resistors. So each stage, or like each of these nodes or points are divided by the amount of resistor you have. So essentially we create a step from the ground from 0 to the V in or V reference. Sorry, from the V ground to the V reference, and then that's basically divided by how many resistors you put there. So, for example, if the reference here is, say, 7 volt, then we have this point will give you, 1 volt, 2 volt, 3 volt, etc. So this is controlled through an additional 3-bit, so that Okay, that's actually not that important. Let me think. So basically, it's using, it's very fast, and then each of these give you a stage at that point. So if, say, you have a voltage input coming in, and then it basically just quickly decide which range that it is, and then pick the closest one to the 3-line controller there. So this is essentially a 3-bit ADC, flash ADC configuration. The obvious drawback in here you can see is it uses a lot of hardware, but the good thing is it's like super fast. Basically 1 clock cycle, and give you the result you want. Any questions on this? Okay. So also generally speaking, how do we convert the voltage to different steps? This is the same for ADC and DAC. Basically, depends on how many bits we have. That gives how many steps we have essentially, and then we just divided the reference voltage to this value, and then we get how many voltage changes in each of the steps, and that's essentially the resolution you're gonna have. And you can calculate it, the digital output. This is ADC, so you can also calculate these outputs from basically what's your input, what's the current voltage versus how many bits you have, and then convert that into a digital value, binary value inside of your chip. Any question on that? Okay, so we also have different, we also have 2 other slightly more complicated configurations. The first one is obviously the one we just talked about, the easiest and most straightforward one. But the voltage divider approach was used heavily on the DAC configuration. anyway, for the other two ways, the single slope integrator and the star, basically the single slope integrator, it basically converts the analog voltage input into a digital value by measuring the time it takes for a capacitor to charge or discharge to the input voltage. And we can see it basically somewhere here. And there's some tricks down using like current source versus voltage source so that we can make this line to be linear. Although I think if you guys took circuit class before, the capacitor charging would be like a exponential, but if we use the current source, it's actually linear. We're not going to test you on that, but it's just know that this time for this type of ADC is a linear slope. That's why we can have like a pretty decent accuracy and converting speed. So essentially, it's just doing the comparator on whatever your current analog input is versus with the current charging voltage. And whenever those two equals, you use that time as the variable to determine what's the digital value corresponding to that. And we also have the SAR. It's basically, it's kind of similar to the previous one, but it does a little bit fancier things. It uses the DAC in here. Essentially, what it does is it does like a binary search to convert for this analog voltage to digital value conversion. So the ADC will approximate the input voltage step by step, and starting from the most significant bit. So imagine you have, say, the reference range from 0 to 3.3. The input was, say, 2. Then the comparator here does comparing this input to half of the reference voltage, which is 1.65. And then if it's higher than that, it does another half of that. So like 1 bit at a time, it calculates, it trying to search until what's the closest output within the amount of bit it has, and then use that as the digital value into the system. Yeah, which is achieved through the digital to analog converter. Yeah, essentially, doing 1 bit at a time and then trying to determine whether to go high or low on the next bit depends on the result on the comparator. Any questions on the SAR or the single slope or the flash? I guess it's good to have this one. So if we do compare the different between these three, basically resolution-wise, the slope integrator is pretty high because you can just, it's like a pretty linear, and depends on how many cycles you assign, depends on the capacitor values you choose. You can have essentially a much very high resolution. As well as the SAR, it's kind of good to high. It's close to the slope integrator, a little bit worse. The flash one is the lowest one because it uses a bunch of hardwares. And then even with the configurations we saw before, that's only give you like 3-bit resolution essentially. And the speed, the flash is going to be super fast. The slope integrator is going to be slower, especially if you're trying to do like higher accuracy. The time it takes to charging and decharging the capacitors will slow it down. And the accuracy, the slope integrator have high accuracy because you can just throw more cycles to it, as well as you can do what they call like charging and decharging at the same time. So that kind of give you a better value of how the curve, give you like kind of check the value twice kind of thing. We're not going to test you on that, but just aware that the slope integrator is able to generate high accuracy signals at the cost of being slow. And the power consumption, I think it's pretty straightforward because a lot of hardware was stored inside of the flash that make it high, and the SAR, because of the DAC components, etc., was involved. That's like kind of like a median, and the slope integrator is just charging and decharging and doing the clock. The clock virtually costs no power because that's like the one thing that microcontroller or any computer is good at is counting clock. And yeah, the cost-wise, again, Flash is pretty high cost because all the hardware components needed. Any questions on the ADC so far? Yes?
I'm just wondering if we should have this chart memorized for the exam.
Well, remember the speed, I guess? Yeah. Any other questions? Okay. So next we talked about the DACs. We talked about 4 types, but they are essentially built around very similar ideas. Oh, well, 3 of them are built on very similar ideas, except for the first one. So let me just show you the 4 types here. So the first here, it's essentially using the PWM signals, characteristics of duty cycle length, or like duty cycle value, will cause the RC circuit here to charge or discharge. So imagine if you have a PWM signal with gradually increased duty cycle, that gives you a equivalent output of a gradually increasing voltage. So with that, when that happens, it just goes up, and then if the PWM signal gradually decreases its duty cycle, it goes gradually down. So if you do this at a very precise and fast way, you're able to get like a sine wave signal. So that's essentially how this works. Any questions on the first type? Basically the PWM plus a low-pass filter DAC, the DAC configuration. I think the DAC, we just covered it 2 days ago, so hopefully this is still pretty fresh to you. We also have the voltage divider, which, using the voltage divide circuit, we will provide that inside of the data sheet. It's kind of important, but yeah. So for this one, it's essentially, you will see these are a bunch of like CMOS shifts, but you can just imagine them as switches that goes up and down. Essentially, this will go down one at a time. You can't do multiple because it's controlled by, for example, this one only 2-bit. And then similar to the Flash ADC, each of these points corresponding to a value that's being essentially evenly divided by how many number of resistors you use. And the good thing about this type of DAC is that it's relatively easy to build, although it takes a lot of components. But because it's using the same value, so it's actually easy to build and with high accuracy. And the next 2 type of DACs are essentially different ways to make the number of resistors smaller so that we can take less space while achieving the same amount of accuracy, or giving a same area that these 2 types will be able to achieve higher resolution. It's not necessarily more accurate, but it's higher resolution because it's able to put in more bits inside of this. But because these 2 uses different values of resistors, it's a bit hard. It's harder to maintain the accuracy of each of these values, so that the voltage divider circuit might not perform as well if we just use the same value massively manufactured, which usually give you a better result. Any questions on these ones? You guys still remember these, right? We covered it on Tuesday, so hopefully, yeah. Okay. Yeah. So normally this type will give you like 2 to the number of n, given any 2-bit accuracy. 2-bit resolution, 2 to the n number of resistors on this one. This one give you a little bit depends on how you configure it, but generally 2 times n plus 1 on the RF here, which is used for voltage dividing. And on this one, it's basically n plus 1, n-bit a n-bit DAC configuration. Any questions on DAX? Okay, cool. So then we're going to jump to the recap. Yeah, as we said, technically you're going to cover everything. With the ISA table, we're going to just give you the whole thing as before, the tool chain, the figures. So those parts will be the same in the datasheet. So whatever you have access to during the midterm 1, you have access to during the midterm 2, just in case. Memory in and out, I hope that's something, with all the labs you have done, that's something already echoed in your memory as well. So you don't have to, worry too much about that. And the midterm will basically be mainly on the last 4 topics that I covered. Yeah. Any questions? Any last minute questions? Before we, yes.
Sorry, could you go back and repeat how many resistors would be needed for each EAC? Like,
Yes. So at any given n-bit DAC, the voltage divider will need 2 to the power of n number of resistors, and the R2R ladder will need 2 times n plus 1, which is essentially, every one branch here needed 2 resistors, and plus that one, RF for the voltage dividing in the end. Yeah, and for the binary weighted resistors, because the value of them are just basically divided by half each time, and then that's basically the number of bits, basically n plus 1, the number of resistance needed for a n-bit DAC design. Any other questions regarding these topics or general exam logistics, etc.? All right, perfect. So happy exam tomorrow. Let me know if you have any questions. Feel free to come down and talk to me, or go to the open labs tonight and tomorrow morning. Make sure if you have any questions, post on Piazza so that everyone can learn on it, and then we will try to answer as many questions as possible. Thank you. Yeah.
Maybe because I received packets that also received what's happening. You can follow up. Yeah, I control cars. I
Comparing multiple that's the answer. One packet, appropriate, and one packet.
Oh, okay, so like 2 questions, like this offset is 0, this offset is like 1, 0, and then also like why do they like
No, well, this is just, it says the phone diagram, it's just because it's on my phone, it looks very good. So this is the thing, and then two, you work on the other.
All these are, they're not. Two separate.
So, if you have